In this video, we take a look at kinetic energy. It's our first form of energy that we're going to quantify. Let's take a moment and refresh our memory on things that we talked about early in this unit. We talked about there being many different forms of energy. We could say that energy is stored either in movement or it's stored in position. We're going to focus on this video by looking at kinetic energy. That's the energy of large-scale moving objects, such as that runner there. Let's go ahead and take a look at our slide now. Kinetic energy. Objects in motion have the ability, as they slow or stop, to do work on other objects. And you recall that work is the means by which we transfer energy between objects. So kinetic energy is simply the energy of motion. That's what we call this. An object's kinetic energy is equal to the amount of work it can do on something as it exerts force while stopping. Let's take a look at this picture over here. This person moving along, and they're moving along with a certain speed. They got a certain mass. It takes 500 newtons of force to stop their motion when exerted over 10 meters. That 500 newtons times 10 meters is 5,000 joules of work. Therefore, we define the object's kinetic energy up here as being 5,000 joules, since that is the amount of work it can do on something while it exerts force while stopping. So that's the definition. The kinetic energy definition is very strongly related to a transfer of energy. Now we can write this as an equation. Kinetic energy is 1/2 mv squared. I like to use Ke as opposed to E sub k, but the kinetic energy is measured in joules. We have that 1/2 multiplier there. The mass must be measured in kilograms, and the speed measured in meters per second is squared. Now you might remember another quantity that contained an m and a v. We call that quantity momentum. Now, in contrast to momentum, kinetic energy is directionless. It doesn't have any direction with it. It is a scalar quantity. Momentum was a vector, so we had to be concerned with which way the object was moving to be able to uniquely describe an object's momentum. Here, we don't need to. Okay, so kinetic energy is a scalar quantity. Up here, let's take a look at this picture. Perhaps you've seen some wind turbines at work. What those wind turbines are doing is they're harnessing the kinetic energy of the winds. Now, as the winds go and hit these turbine blades, the wind will slow down as it passes through. What those turbines are doing is they're extracting the energy of motion from those winds. Of course, they're using that to turn the generator inside to generate electricity. Let's go ahead and take a look at this strong dependence on speed. Kinetic energy increases with the square of the speed, and I can see that right here. Since I have a speed squared in that equation, we see that there's a very strong dependence on an object's speed. Doubling your speed will quadruple your kinetic energy. Tripling your speed increases your kinetic energy by a factor of 9. Over here we have this graphic showing stopping distances in relation to the speed. Since stopping distance is proportional to Ke, you're going to need 4 times the distance to stop when you're traveling twice as fast. Similarly, you would need 9 times the distance to stop if you're traveling 3 times as fast. Again, we go back to the dependency on speed squared. Let's consider mass now for a moment. Let's say that 2 cars, one has mass m, the other has mass 2m, traveling with the same speed. How do their kinetic energies compare? How about the stopping distances required to be able to bring those cars to a halt? We take a look at the equation. The equation says that there's a mass in there, but it's only to the first power. So for these things, we see that twice the mass would have twice the kinetic energy. It would take twice the distance to stop. Let's go ahead and try a few calculations. Here we have 4 problems that we'll look at. We have this car, mass 1,200 kilograms, traveling at 15 meters per second. Looks like it's going up a ramp. How much kinetic energy does the car have? So let's go ahead and just start with the equation. Write it out so we remember what to do with these numbers. 1,200 kilograms multiplied by 15 meters per second, and I'm going to square just this number. I take a look at the units, make sure that those are the appropriate units for the kinds of quantities I'm looking for. It looks like mass should be in kilograms, speed in meters per second. That's going to give me kinetic energy in joules, so I'm all set. When I go through and plug those numbers into my calculator, I get 135,000 joules. So quite a bit of energy associated with that car's motion. Let's take a look at number 2. Cheetah, fastest land animal, reaching speeds of up to 60 miles per hour, it's about 27 meters per second, at least in short spurts. If its mass is 75 kilograms, how much kinetic energy does it have? So again, same basic idea. Kinetic energy, 1/2, 75 kilograms multiplied by 27 meters per second squared. And for that, we get only 27,337.5 joules. Still quite a bit. The object's moving pretty fast there, but nothing in comparison to that car. Now, number 3 is a problem that we could solve in a variety of ways. How many 75 kilogram runners moving at 3 meters per second are needed to have the same kinetic energy as this over here? So this thing's got a fair amount of kinetic energy. Over here, we just have a bunch of people that have much less kinetic energy, but when I'm done, I want to have the same amount of total kinetic energy as that cheetah. So the question is how many of these people are needed to have that much KE? We could do that in a couple ways. One way I could do that is I could find the kinetic energy for one person, and then take this number here, divide it by the number that I get here, and that will give me the number. Another way that I could do that is to consider that both of these masses are the same. We have a 75 kilogram cheetah and a 75 kilogram person. They both have the same masses, and if I look at these speeds, I see that the cheetah is 9 times faster. That means I would need 81 of these people to have the same kinetic energy as that single cheetah. And that's, again, because of the dependence on the speed squared. Now, if you're not sure if you buy that, let's go ahead and calculate the kinetic energy of a single person and see if that actually works. And for that, I get only 337.5 joules, and that's per person. If I take that 337.5 joules and divide that by 337.5 joules per person, I get 81, as I expected. I guess I write it as 81 persons. Number 4, last problem. How fast must a 146 gram baseball be thrown to have the same kinetic energy as a typical bowling ball that has a kinetic energy of 67 joules? Now, that bowling ball, quite a bit more massive than this. That baseball, less mass, but probably thrown a lot faster. Let's see how fast we'd have to throw it for it to have the same stopping power as that bowling ball. So I'm going to set the kinetic energy of the baseball equal to 67 joules. And let's go ahead and calculate that speed by using that kinetic energy equation. Notice I am converting that into kilograms. Easiest way for me to solve this is to, for me, I'm going to multiply both sides by 2 to begin with. That gets rid of that half. Then I'm going to divide both sides by 0.146. And now I just have to get v is just the square root of 2 times 67 divided by 0.146. And for that, I get 30.3. What kind of units do I get here? Well, the nice thing about this is that if every quantity that I'm working with is using the appropriate SI units, I have my mass in kilograms, and I have my energy in joules. That means that my unit for speed should come out in meters per second. Now you could certainly go through and check that by breaking those units down, the joule and the kilogram, breaking those things back down into their to their base units, and you could see that in fact it does reduce to meters per second. So there we go, 4 problems for you on kinetic energy, and that completes this video.